In the previous chapters, we were taking light as a ray. They were going straight like a bullet. They do not interfere with each other. For example, one ray is going here and one ray is going here. And now see, here is a meeting point, right? They're meeting here, but nothing fancy is happening here. But what if we take light as a wave, like a water wave? They do interfere. For example, here is one wave coming at this point like this, and other wave is coming like this. They're meeting here. At this meeting point, interference can happen. They will interfere with each other depending on how they meet. They can create stronger waves or weaker waves. They can get stronger or they can get weakened. So this interference, which we are going to talk about. And before going that, let's discuss some of the technical terms with the wave. If we want to create a water wave, for example, we throw a stone in a pond, you will see such pattern. So it can look somewhat like this, and this will continue, the cycle will continue. And we can say the wave is going in this direction. The uppermost point at this moment of time, if I take a picture of this wave, I can say this point is crest. Crest means the maximum height from the equilibrium position. Equilibrium position is the resting position where the water was before you made the disturbance. The lowermost point will be called a trough. Now, so what wavelength will be? It is the distance between two crests, or it is distance between two troughs. Let's read the definition of wavelength. It is a distance between two consecutive, one after another, points on wave which are in phase. Now, this is an interesting word, phase. What do you mean by that? So, every point on this wave, we can assign one angle, and we can say that point has that phase. For example, if this is 0 radian, I can assign a pi here. So this point is at phase pi. So one pi is completed. You can think of like that. One piece a piece, one pi is been finished here. After that, another pi, but upside down. But if you mark this point, it is 2 pi. So 2 pi have been completed, and we can assign like that. This point we have assigned angle, this point, and this point. Other points also similarly. If you cut a pi in a half, you will say this is pi by 2. And after this, what will happen? Now, one way of thinking like that, the wave will repeat. So I can again start with a 0 here. 2 pi, I can take it as a 0 again. So what will be this phase? This will be pi by 2. Right? Again, the pi will complete. And here it will be 3 pi by 2. And here it will be again 2 pi and it will repeat. So what I've done is small reset I have done. After 2 pi again, I have started counting with 0. So if you note down the crest, consecutive crest, their phases are same. And you can see with the angle. And also we said, I know you can take between two troughs also. Let's see why that phase is same. So if it is pi or 2 pi by 2, I can say 1 pi by 2 is this side, 1 pi by 2 is this side. What about phase of this point? So I can say 1, 2, 3, 3 pi by 2. Again, after 2 pi, when cycle is completed, I'm resetting it from 0. And I can say this is pi by 2, this is 2 pi by 2. And what about this point? Again, 3 pi by 2. So they are also in phase. Physically, we can think like the point in phase will be, there'll be two conditions. One is same distance from equilibrium position. And the second thing is same motion. Motion, I mean, they are going in the same direction. So if this point has become crest, it will come down. This point has become crest, it will come down. That is the future of it. Like this is just a picture. If you play the animation, you'll understand this point will come down. So they are at the same distance. And also their motion, the direction of motion is downwards. So that's why they're in phase. What about this point? If you take these points, they are the same distance. And the future is they will go up now. They have come to the lowest point. So they'll go up. So that way we defined the wave length. And also you can see it as a top view also. This is a side view from the side view. And if you see from the top view, you will see, circular pattern. So that is shown here. So here it is a crest. So you will see from the top like this. Here is a trough. I've shown it by, dotted lines. Here is again the crest come. So here it is. So distance between these two. Okay, this picture is also given. The top view is also given. So we have to measure the distance between them. It will be the same as we are calculating from the side view. So that way you can calculate the wavelength. To understand better, we are taking a help of animation. It is a free animation. You can also play around. So what it is a water pond. Here we are seeing from the side view, and this is the equilibrium position or resting position of water. So I will start this tap and it will create disturbance, and you will see waves are formed. Let me pause it. So this was the equilibrium position, and if you see, this is the crest and this is the trough which are getting formed, and the cycle continues. So if you want to calculate what is the wavelength, we just need to calculate the distance between two crests. So this and this, we can measure it, or we can measure it between two troughs. What if we see it from the top view? Let me give you a picture. So if I just pause this and if I flip it to the top view, you will see that one crest is forming. and then there is a trough, and then there is a crest. Let's see. So I will switch it to the top view. See, this crest is forming, then the trough, and then the crest. So these bright rings which we have shown, it is crest. We also call them wave fronts. Then again trough comes, and then again the crest comes. So it will continue. We can also visualize waves going like this. So if somebody asks, can you calculate on the wavelengths by this picture? Of course we can. What we need to do is we need to calculate a distance between two crests or between two troughs. So that way we are able to visualize waves better and the wavelengths better. Now we will discuss the frequency of a wave. We discuss frequency when there is something periodic, cyclic. For example, if you are going to school, you're going to school and coming back, you're completing one cycle. So if you go, like say, 5 days a week, then 5 becomes the frequency of you going to the school. Similarly, here, number of wave cycles passing through a point per second we call a frequency. This is a point, and will observe like if one how many wave cycles are we crossing here per second. So the time is important. Whenever the frequency we are talking about per second, per unit time. So if I count 1 second, I'll see only this much wave has gone through. So one complete cycle has gone through. So the frequency will be called 1 hertz. What if I observe this point, and instead of two waves cycle, or two wave life cycle, you can say, or two wavelengths actually have been crossed, I will say here it is 2 hertz, right? So this wave is of frequency 2 hertz. Again, now you guessed it, if it is three are crossing through, and then I will say the frequency is 3 hertz. Hertz is also, we say it as a per second, or you can say cycles per second. But hertz is the name of scientist, and we, instead of saying per second, cycles per second, we say hertz. So 3 hertz means 3 cycles from a point per second are passing through. Now, what if only this much of wave is passing through? So if you say, oh, the cycle is not even one cycle is completed, right? Only half of the cycle. So I will say 0.5 hertz. So that way we define frequency. Let's also understand frequency by this animation. So this is the frequency as of now. Actually, how much frequent your disturbance in this water is. Now what I'm going to do, I'm going to increase the frequency, and you'll see the change. The drops are more frequent now, right? The cycles are completing faster. And if I decrease it, now I have lowered the frequency, you will see this. So this way we can understand the frequency too. Now let's build a relation between the wavelength, frequency, and the speed of the wave. And we are talking about the light wave, and light speed in vacuum is constant, 3 into 10 to the power 8 meter per second. And here is a relation between them. C, which is a light speed in vacuum, we can denote this by letter C. This is a constant, and here it is a product of lambda and frequency. Lambda is a wavelength, and frequency is denoted by small letter f. So if this guy is constant, it means their product must be constant. And if we need to keep the product constant, we can say lambda and f will be indirectly proportional. So if you increase the wavelength, the frequency will decrease. If we decrease the wavelength, the frequency will increase. As we have discussed, like, for example, if I say 2 into 4 is equal to 8, if I need to keep this product constant, and if I increase this, let's say I increase 2 to 4, I have to decrease other thing to keep my product constant. There is no other way. If I, for example, if I decrease this to 1, I have to increase 4 to 8, because I need to keep my product constant. So whenever we get formulas like this, and one thing is constant and these things are in product, they will have the indirect relation. And this is beautifully seen in our simulation. We will see when we change the frequency, the reverse effect will be on the wavelength. Let's see. So this was the frequency as of now, the disturbances which is happening, and you can also see how much the wavelength is. So what I'm going to do, I'm going to change the frequency. So first, let me increase the frequency. So I'm increasing frequency, you will see the wavelength will get shorter. So if I'll make it to the maximum, so the disturbances are more frequent now, but you will see that the wavelengths are getting reduced. Now let me go to the other extreme. I'm lowering the frequency, I'm reducing the frequency, the disturbances are very less. Now you will see the bigger wavelengths. Now we will talk about the interference of waves. So when two light waves will meet at a point, interference will occur. There can be two kinds of interference. It can be constructive, they will build on each other, or it can be destructive, or they will destroy each other, nullify each other's effect. So if we are talking about the first case, here is the first wave, and here is the second wave, and they are meeting here at this point because they are in phase. Both points at here are in phase. If this guy is going up, the other guy is also going up. We can say here they are meeting in phase. The phase difference is nothing or zero. And due to this, the crests will align with crests. So if you see here, so this is a crest of this wave. So this will align with this. The trough will align with the trough. Again, the crest will align with the crest. So due to this aligning, we can see we are getting a stronger wave. They built on each other. So they were, if you see, this wave was this much, this wave was this much. So when they were on top of each other, they built it up. So this is called constructive interference. And now the second case, they will destroy each other. How? This is a wave. So note this point, it will have some wave of this black color line. The other wave is coming like this. It is just flipped, kind of a mirror image. So the crest of this wave is meeting the trough of this wave. The crest of this wave is meeting the trough of this wave. So it is the exactly opposite scenario of the constructive interference. What is happening? These waves are meeting out of phase. The phase difference is pi or 180 degree. And when then that will happen, the crest will align with trough as we have seen. And due to that, take this example, like this is a wave, one wave is like that, and one wave is like that. They will result in total destruction of each other. Think of it like this wave is trying to pull it up, and at the same time, this wave is try to pull it down. So what will happen? The result will be the equilibrium position. You will get the flat surface, nothing, no waves. Here, this part of wave is trying to pull it down, but because they have overlapped such, so this crest will be on top of it, so it will try to pull it up. The result will be like this. So we'll get nothing. So this kind of phenomena we call interference. This will only happen when we consider light as wave. Now we will understand Young's double slit experiment, which established that light behaves like a wave. How it establishes, let's see. Here is a setup. We have a light source here. Let's say we have a red laser, which we are shining. And we have double slits here, two holes, two slits, which are separated by distance d. So you can say the distance between two slits is given by small lettered d. Let's say the light source had a wavelength lambda, and after a distance L, capital L, we are keeping a screen where we are recording what is the pattern, how these two spots will look like here. Now, if you think light as a ray, what we should expect is there should be one bright spot in front of this and one bright spot in front of that, because light travels straight. It should go straight. One bright spot will come here and one bright spot will come here. But see here, we are getting a pattern. We are getting alternate bright and dark fringes. So there is a word, fancy word, fringe. We are getting fringes here. Now, why that is happening? Because the waves are interfering. Interfering with what? For example, if this wave, this hole creates a wave, now we are thinking light as a wave. So I have created three crest wavefronts here and also three crest wavefronts of this slit. And they will go forward at the same time because they are the source of the same light source. So now, if you can see some points here, look at this point. What this point says, crest of one wave is meeting the crest of other wave. So what does that mean? Constructive interference. Another point here, crest of this wave is meeting the crest wave, this wave again. So these points, if I can draw more wavefronts, you will find out that crests are meeting crest. It means the troughs are also meeting troughs. So what will happen? The constructive interference. That's why in front of that, you will find the bright spot. So what is happening here? Here is the constructive interference is happening. Waves from two slits are aligning perfectly, crest with crest and trough with trough. That's why we are able to see the bright band here. Okay, what about this point? So this point also we can understand. This is as a dark spot, or you can say of no light area, nothing is coming, and that happens when we destroy. Somehow they are cancelling out. These waves are cancelling out each other's effect. So that happens because of a destructive interference. Let's see. So here I have for this slit wave, I have drawn the trough also because a trough will be sandwiched between these crests. So these dotted blue lines, I have shown the troughs. Now, can you figure out some points where crests are meeting the trough? So see, this is the crest of this wave, and it is meeting the trough of other wave, this here, right? What about this point? See, the trough of this wave is meeting the crest of this wave. So in front of that, you will get the dark spot. So here, what is happening is destructive interference. Destructive interference. And now, if we have this pattern, what we want to look forward for? First thing we can explain like how they are spaced out, how these bright bands are spaced out, and how we measure that. We can measure, let's say, this is the central band, okay, central bright band, and the first order band. It's fancy names. So this is the center because it is at the center of these slits just in front, and this is the first bright band after the central one. If you measure the distance between them, we'll call it fringe width, and we can denote it by x. Let me name it. So this is this band, we will call it first order bright band. So it will tell like how these bright bands are spaced out in the result we are getting, in the interference pattern we are getting. And it will be similar if we are calculating x, the distance between this central band and first order bright band here, this side will be same. It will be perfectly mirror images and it will go on. It will not change. This distance will not change. And if you see, there are four variables here. First is this x fringe width. Then we have distance between the screen and the slits. Then we have a separation, how much we have kept in the slit, and then the wavelength. Here's a relation between these four variables. So this x, or we can say how much the bright bands are spaced out, or what is the distance between the central bright band and the first order bright band, that is given by x. That will be directly proportional to the wavelength of the light source. So it will be equal to lambda, and it is also directly proportional to the distance between the screen and the slits. So we denote it by L. And this gap, this x, will be indirectly proportional to the distance between two slits. So that we can denote it by small d. Because it is indirectly proportional, it will be like this. So this is the formula we are getting for Young's double slit experiment. Now we will do the double slit experiment here with the simulation and see whether our understanding is making any sense here. So we have two light sources here. I'm not showing two slits. You can think of it like two slits here. One is here and one is here. And there is a separation between. And then there is a screen here. So if I on the light, this light and this light, it will interfere. They will go at the same time and they will create some pattern here. So let's see, first let us on this. So this is the pattern which only this point source is giving. So these are the crests and the darker one are the rough. So let me start the other one also so that we can get a pattern. As of now, if you see, we will not get much on the screen. We are just getting the light source here bombarded here, right? But now if we start the second one, you will start seeing the pattern here. So if you can see, this line is getting constructively interfered. And in between these areas, if you see in the dull areas, those are the destructive interference. And now when they reach the screen, you will be able to see the fringes, bands. So what is happening in front of this screen part, what is happening? Constructive interference is happening. The crest are matching with the crest. And in front of this dark fringe, what is happening is the destructive interference happening. Or one of the waves crust is matching with the trough of other wave. So that's why we are getting the dark spot here. They are canceling out each other. Now the interesting part will be if I play with the wavelength, I play with the separation between these two, what should happen? So if you see here, the green color we are using. So if I increase the wavelength, let's say red color has more wavelength, what should happen to these fringes? Will they be spaced out farther away or they'll become closer? So our formula for the distance between the central band and the first order band is x is equal to lambda L divided by d. So it is directly proportional to the wavelength which we are using. So if red color has more wavelength, we should be able to see the distance more. So let me play with that. Let me put red and let's see if we are getting more spaced out interference pattern. Let's see. So now you can see the distance between the central band and that one is not also coming completely on the screen. So that has been increased. What if I decrease the wavelength? So red has more wavelength, and if you see blue color has less wavelength. So we should be able to see the interference pattern where the central band and the first order bright band will come closer because they are directly proportional. Let's see. So with a blue color, so when they reach here, see, they are coming closer, right? So the distance between the bright bands is now less spaced out. They are fitting together. They are coming close to each other. So now let's play with the distance. So if I decrease the distance, it has an indirect relation between the fringe width. So if I keep it like this, let's understand how much it is coming right now. So okay, around that. So this is the distance, this much how they are spaced out. Now what I'll do, I will decrease this distance. Let's see what happens. So let me decrease a little so they will become closer. So if I do like that, central band will come here, but let's see where the first band comes. That is not even coming to our screen, that has gone beyond. So you can just see the haze here from the starting band of that bright band. So that's become huge. The distance becomes less, the fringe width becomes huge. What if I separate them more? So I increase that small letter d or the distance between the slits. What should happen? The interference pattern will come as the bright bands will come closer. Let's see. So I will start this and let's see what happens here. See. So the distance between the central band, this is the central band, and the first order bright band is this, the distance will become lesser. So you can play around with this simulation and understand the formula even, that how it impacts and how we can get a different kind of pattern depending on the distance between the slits and the wavelength we are using.